Hi, and here we are at section 8.1 talking about simulation. So real quick, think of a way to use random number table. So I have an example down here, random digits, that you can simulate 100 trials of flipping a coin. Now flipping a coin might be a little bit tedious if you're doing it, you're actually flicking the coin, it's landing on the table, and you're noting what came up. So we can use random number generators or random number tables to simulate that. Now, flipping a coin, we talked about the probability. If it's a 50% chance of heads and a 50% chance of tails, we know that those are even probabilities, 50 and 50. So now when we go to assign digits to it, you think of the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. There are 10 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 1 through 9, and then 0 would be the 10th digit. So there's 10 digits there. So now if we got a situation where we've got 50% heads and 50% tails, what we can do is we can look at that, we can say, okay, 50% of the digits. So we can say, 1, 2, 3, 4, and 5. So 5 of these 10 digits can be a heads. So we've got the heads, that's going to be the digits 0 through 4. And then tails is going to be the other ones, 5, 6, 7, 8, and 9. So we know that tails can be 5 through 9. So now, if we want to simulate 100 trials, what we can do is we can just look at, obviously I only have 10 numbers down here, so we need more, but what we can do is we can look at this 6, go up here and say, okay, this first one is a tails because it falls in 5 through 9. So this first one would be a tails. This second one, which is a 4, would fall for heads, so it would be a heads. 3 would be a heads, 7 would be a tails, and 4 would be a heads. Now see how this is quicker than actually flipping a coin. You don't have to chase it down, you don't have to pick it up, flip it, and run with it again. So we're simulating flipping a coin here. This would be tails, this would be tails, this would be heads, this would be heads, and this would be tails, right? So now you would continue on in that manner for as long as it takes to get to your 100. So that would be flipping a coin. Now rolling a number cube is going to be a little bit different because it's not as a straight up 50-50 chance. Now what you can do though is you can omit certain numbers as long as you have the same numbers assigned to the same probability. So let's look at a number cube real quick, come up with a probability model. Well, the probabilities of getting a 1, a 2, a 3, a 4, a 5, or a 6, well, they're 1/6, they're 1/6, they're 1/6, they're all the same, and they're all 1/6. Now, we can't break up 10 digits. If you look up here, our digits 0 through 9, we can't break those up in a way that is nice with 6, right? Because it's like 16.67% for that, so we can't break that up. But what we can do is we can look at this and we can omit some. Like for instance, we can say, well, it's all the same probabilities. So we can say, all right, let's not look at the 0, let's not look at the 7 through 9, and now anytime we get to a 0 or a 7 through 9, we can skip over it. And what that is since they're independent entries, we can look at this and just, okay, whatever number comes up is the number. So we can say that if a 1 comes up, it's 1, if a 2, if a 3, if a 4, if a 5, and a 6. A lot easier than breaking it down and saying, okay, 1/6 of 10 digits. Well, all of a sudden we're looking, 2, 3, 4 digits at a time to try to make it work. What we can do is, okay, you get to a 6, we know that this is a 6, we know that this is a 4, we know that this is a 3. 7, we're just going to skip over that one. We've got a 4, an 8, skip, a 9, skip, a 2, a 1, and a skip. So what you can do after one, this doesn't count for a roll, this doesn't count for a roll, this doesn't count for a roll, this doesn't count for a roll. So after 3, 4, 5, 6 rolls, you've got, a 6, a 2, 2 4s, a 3, and you can go up that way. So it might take a little bit longer because you are going to skip over some numbers, but what you're doing is you're forcing it. By skipping over those, you're forcing it to match up with the numbers you have there. So that's just one way that you can go about doing it with a number cube, where you know omit some numbers from there. So simulation, we talked about probability models a little bit, so it's not feasible to repeat certain tasks many times to gather data on probability. So we can use probability model to simulate simple, like flipping a coin, to complex events. I've got a pretty complex event with kidney replacement and dialysis coming up here in just a second. So you can see that that's obviously not a simple situation, but knowing the probabilities and having the probability models, what we can do is we can simulate many, many trials. So simulation is imitating a chance behavior using table. We have technology now, you know, to do this, to do those many repetitions quickly. But you're familiar with the random digit table and random integer generator. You can, you know, go to Google or whatever and type in random digit generator, and you find many number generators there. In computer software, you know, we'll handle some of the more complex ones where you enter the information and it actually runs it for you. But we're just going to keep it pretty basic here with random digit tables. Now, independent. Two random phenomena are independent if knowing the outcome of one does not change the probabilities of outcomes of the other. So example that we can use here would be probability of rolling a 6 on a number cube. Okay, probability of rolling a 6 and then a 6, actually, we can look at this, and then a 6. So we're going to roll a 6 and then a 6 is what we want. And what we can do is we can find the probability. Now, independent, the number cube doesn't know what just rolled, right? There's no brain in the number cube that's keeping track of things and saying, hey, you know, it's I just had a 6, I got to be something else, right? It's random, it's independent. It doesn't care what just happened because it doesn't think. So independence, if you take a look here, there's a 1 in 6 chance that you get a 6. There's a 5 in 6 chance that you get a not 6. Now, from there, your probabilities are the same. Regardless of whether you rolled the 6 or not, there is a 1/6 and 5/6 chance that you get the 6 and not 6 respectively in each of those paths. Now, everybody's going to take a little bit of a different path here, depending on what you roll. So you could go here and you could get a not 6, well, which 5/6 of the time you will. And then you could get a not 6 again, or you could get a not 6 and a 6, or you could get a 6 and a not 6. So there's 4 different paths you can take there, each having their own probabilities. Now, the probability of a 6 and then a 6, remember, you multiply the probabilities. So your probability of getting 2 6 in a row is 1/36. So not very good chances. Probability of getting a 6 and then a not 6 and then a not 6 and then a 6 is, well, it's going to be the same, right? Because multiplication is commutative and you're just multiplying the probabilities. It doesn't matter what just happened, whether you got a 6 or a not, it's gonna happen with the same probabilities. And then the probability of getting a not 6 and then a not 6, well, there's 5 of the 6 are not 6, so you're going to multiply those probabilities. Now, once again, note that all of these probabilities are going to add up to 1. While it's unlikely that any given number is going to come up, something is going to come up. So you got 25, you got 10 more here, you got 35, 36 out of 36 it totals up to. So independence, knowing the outcome of one does not change the probabilities for the other. You can roll a die and you can say, okay, what number's coming up? And you don't have to say, well, it depends on what just happened, right? You can say, what's the probability of rolling a 6? It's the same every time. It's like flipping a coin. Not independent now, probabilities at one stage depend on the outcome of the preceding stage. So if I was to say, okay, you know, somebody just took a ball out and I said, what's the probability that I get a red? I would say, well, it depends. Because if you look at stage 2 here, in one of them there's 3 of the 4, and in the other there's 2 of the 4. So I would say it depends, and I would say it is not independent because it depends on what just happened. So the probabilities at one stage depend on the outcome of the other. I can't answer, okay, if Joe Schmo took a ball, I can't answer, okay, what's the probability that you get a red without knowing what Joe Schmo picked, right? I would say, well, it depends on what Joe Schmo had. So taking a look here, you've got different paths and different probabilities. You've got, 2 of the 5 are blue, so there's a chance that you get, 2, 5, and then all of a sudden you take a blue out, and now 3 of the 4 are red, or 1 of the 4 is blue. Now if you take that out, 0 of the 3 are blue. So 0 of the 3 are blue here. If you took a red out at the second stage, well, 1 of the 3 if you took a red and then a red. If you took a red and then a red, well, that would, you would have two of the blues remaining there. So now, one stage depends on the other, so you need to know what just happened in order to make a decision there. So setting up a simulation, we kind of did this with the coin flip at the beginning, so we'll move quickly. Give a probability model. So Shaq is a 50% free throw shooter. What is the probability he makes 3 in a row out of every 10 he shoots? So now, each free throw is 50% make or 50% miss. Free throws are independent of one another. So that's been shown that free throws are going to be independent of one another. So now, taking a look at this, step 2, we're going to assign digits. So first one, give the probability model. So we would have, for that, it would be a make. It would be a make would be 50%, and a miss would be 50%. So that's kind of described up there. But let's just hang on tight to that for a second. So now, one digit simulates a free throw. Since it's 50%, we're going to do the same things that we had there. So the digits 0, 1, 2, 3, and 4 represent a make, and 5, 6, 7, 8, and 9 represent a miss. So now with that, what's probability he makes 3 out of every 10 he shoots? Well, let's take a look down here. What we're going to do now for step 3 is we're going to simulate many repetitions. Okay? Remember, 0 through 4 is a make, and 5 through 9 is a miss. Okay, 0 through 5 is a make, 5 through 9 is a miss. So reading the table, how many groups of 10 have 3 consecutive makes? So we're going to look at groups of 10. Okay, so let's look at the first one. Remember, a make is a 0 through 4. So we've got a make, we've got a miss, we've got a make, a make, a make, and it doesn't really matter what else happens. And actually, this one has 2 consecutive makes. So we're going to color this one green because this is a success. This is a success right here. So let's look at the next one. We're looking for 3 consecutive makes, right? We're looking for 3 in a row that we have 3 consecutive makes. So I've got make, I've got miss, 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 make, miss, miss, make, make. We started off, but it still didn't finish out. So we're looking, this is going to be a red. So this is going to be a not success. Here, we've got a miss, a miss, a make, a make, a miss, a make, a make, a miss, a make, a make, a make. Once again, this is going to be a red because we didn't get 3 in a row on this 10. So let's look at the last one here. I've got a miss, I've got a make, I've got a miss, miss, make, miss, make, make, make. Hey, we did it. And a miss. We did it. So now the question is, what is the probability he makes 3 in a row out of every 10 he shoots? Well, looking at this, we did 4 trials here in this situation. We had 2 successes out of the 4 total. So we would say 50%. 50% chance that he makes 3 in a row out of every 10 he shoots. Okay, based on our simulations. Okay. Now dependent. Now each one of those is independent because one free throw doesn't change the probabilities of the next. So now setting up simulation here with dependent. So give the probability model. So we've got a kidney transplant, successful 90% of the time, 10% of the time it's not. I know it's a little bit morbid, but that's okay. Now, if you move on to the next stage, 60% success rate and 40% return to dialysis. If it takes successfully, there's a 70% chance you live 5+ years. There's obviously 30% chance you don't. And then dialysis, if you go on dialysis, there's a 50% chance that you live 5+ and a 50% that you don't. So this would be the tree here, and you're using your stages to determine where you're going next, and that's where the random digit generator is going to come in. So this essentially would be stage 1 right here. So this would be stage 1. This would be stage 2, and this would be stage 3. So setting it up and looking at the different things, and you can pause it and look at this a little bit more in depth, but based on those percentages we're going to assign, so 90% chance survive, so 90% of our digits are going to go to survive in stage 1, and then one of them is going to go to not, and then stage 2, so if we pass stage 1, we're going to go on to stage 2, and then stage 2 is going to send us one of 2 directions, with dialysis or without dialysis, or sorry, with success and with dialysis. So we can go ahead and do that. Now let's simulate many repetitions. So what we're going to do is we're going to follow along here, and we're going to look at many repetitions here. So I'm going to keep this one up there, just so we can reference it. So my first one is a number 3 in stage 1. A 3 survives, so we're going to move on to stage 2 with an 8. An 8 puts me in dialysis, so I'm going to go down here to dialysis, and then a 4 says, okay, I survived 5+ years. So my first trial, my first 3 was a success. Okay, next one now, so we're going to start over. Next one, I'm going at 4, so 4 tells me I survive. 8 in stage 2 tells me I'm going to dialysis, and then a 4, so I'm going to go down to dialysis. A 4 tells me I survived 5+ years. So I got a success. 8, 7, 8. So once again, I survive. 7 tells me I go on dialysis, and an 8 tells me I don't make it. So 8, 7, 8, not so good. Okay? Let's see. Look here at our next one. I've got a 9, which is going to put me in the survive, so I move on. I go a 1, which was a success, so that's going to put me to the success batch now, and then an 8. Well, the 8 sends me here, so that does not work out so well. So end simulation. Look at this one. My next one is a 0. Well, take a look at what happens here right away now. If I'm a 0, well, I don't make it to the survive batch. I don't. So that is that, and that is end simulation right there. So then we'd move on with the next one, 3, 8, and so on with that. So how many survive after, after our 4 trials there? We'd say 2 out of 5 made it with that. So that is setting up a simulation, running simulations, and with independent and dependent situations.